Everyone, if you are a HPC developer, this talk may be interesting to you. So I would like to introduce EasyView, which now support a widely used HPC profiler called HPC Toolkit. So EasyView provides a format converter which can convert the HPC Toolkit format into EasyView format and can be directly viewed by EasyView in the VS Code. So in this talk, I would like to show that how we can view a HPC application and show the insights. Okay, so here is the VS Code, and we already installed the EasyView. So we have a HPC Toolkit converter. So this is a Python program, and we already open source that, and one can easily install this on your machine, and that can convert any given HPC Toolkit database into the EasyView format. Okay, the output can be a drcct prop format, and EasyView can directly open that. So in this talk, I would like to use this Laghos as an example, which is a GPU application for the simulation. Okay, so in the code, you can directly open that, and we can see the top-down flame graph by default created by the EasyView. So from the code, from this flame graph, you can see we have mainly 4 steps. Okay, so you can see that probably in the loop, right? And also that we have some initialization part, and underneath we see the full call path that for the code. Okay, so you can see that it's related to the memory operations in the code, and underneath we have some CUDA runtime code that we don't have the source code, so cannot be mapped back to the file. Okay, so this is a top-down view, which means that you can see how the time, this is the CPU cycles consumed from the main to its colleagues until to the bottom. Okay, so you can see that underneath there's some other functions called inside the CUDA runtime. They're related to the log or related to the debug APIs something. Okay. So definitely from the root you can see a overview of the entire program, how the time is consumed in the CPU side. Okay, so we can also have multiple metrics collected by HPC Toolkit be viewed here. So besides these cycles, we also have all of the other GPU metrics here. So we have this GPU ops. You click here, we can have another flame graph. It shows all of the GPU operations. So you can see that this is a call path with all of the GPU operations associated with. So if we click underneath, you can see this is the GPU kernel, right? So this is one GPU kernel here. Okay, so actually there are multiple metrics here. So because HPC Toolkit really provides powerful analysis that collect deep insight into the GPU kernels. Okay, so this is the top-down view. If we go back to the cycles, and we can also do the search if we know that we want to see any function related to CUDA. So definitely you can search for CUDA, and this will highlight all of the function related to CUDA. Okay, so here that you can have a sense how the time consumed in the CUDA related functions, and otherwise is the not CUDA related, possibly the most of the CPU functions there. Okay. And also that we have this bottom-up view, which is particularly useful to identify the hard functions and in their call path. Remember, the bottom-up view is the reverse view of the top-down view. So on the top, you can see this is the leaf function, and underneath will be its callers. So this means that the log weight is called from the mutex log, is called from the cool debug API detach, called from the cool debug API detach again, and called from the cool something, right? So this is the reversed call path. So it's useful to see that, oh, here the log weight can be a hard function, and it can be called by different places in the program. Okay, so if we click here, it can zoom in the all of the colors of the lock weight and see where this lock weight is caught. Definitely, it's inside the CUDA runtime, but eventually it's from the CUDA memory, right? So this means that CUDA memory eventually triggers the lock weight function, and it's caught by other places in the code. Okay, so someone would like to take a look into the program and see why this CUDA memory copy is caught and whether it's necessary or not. So again, that you can see some other metric. For example, let's see this kernel seconds, which means that how much time consumed in the GPU kernel. So here, using this bottom-up view, we definitely can see which is a hot GPU kernel. For example, this one, right? So if you click and it can map back to the source code and see this kernel is the cuKernel 1D, right? cuKernel 1D, and this is the hot kernel, and it is caught by from different places in the program. So this someone would like to look into this kernel and whether we can optimize this kernel or that we can optimize the CPU code to avoid calling this kernel. Okay, so at the end we have the flat view. Okay, it shows all of the hot functions and hot files, hot libraries that you want to look into. For example, you can see that the hot file is this is the forall.hpp, this file. So this is all of the related to the CUDA kernels there. So that's why we measure the kernel at seconds. So this most of the time is consumed in this file defining all of the CUDA kernels. Okay, so this can be useful. Again, that's if you are a HPC toolkit user before and you don't quite like the flame graphs, you can always go back to the tree table view. So which can show all of the metrics in the tree table, and you can zoom, you can drilling down to see any call path. So all of the metrics are associated with that. Okay, and you can also choose which metrics you want to show or you don't want to show. Okay, so this view also supports the bottom up and also the flat view. Okay, so that's for users to use. Okay, thank you for your listening, and we would like to hear any feedbacks to help improve EasyView. Thank you.